Hey everyone! Ever stop to think about what's really going on inside a simple melting ice
Please.
cube? Or, on a totally different scale, how we manage to make enough fertilizer to feed the entire planet? Well, believe it or not, the answer to both is the same. It's all about this invisible balancing act that's happening everywhere all the time. It's called chemical equilibrium, and today we're going to pull back the curtain on this super important idea.
Yeah, it sounds like a riddle, doesn't it? What could a simple ice cube in your drink possibly have in common with a massive factory turning out fertilizer? The connection is this amazing fundamental concept in science, the principle of balance.
All right, so let's get into it. First up, what even is equilibrium? Before we get all technical with the chemistry, we gotta understand the basic idea, this concept of a world in perfect balance.
Okay, so the best way to think about equilibrium is to picture a tug of war. But not just any tug of war, a perfectly balanced one. You've got two teams, and they're both pulling as hard as they can. There's a ton of energy, a lot of action, right? But that little flag in the middle of the rope, it's not moving, not one bit. That's the key to equilibrium. It looks like nothing's happening, but underneath the surface, it's incredibly active. It's a dynamic balance, not a static.
And you know what? This idea isn't just for chemists in a lab. We see this kind of balance literally everywhere. It's happening in the physical world all around us, in ways that are actually pretty easy to visualize. So let's look at a couple of real-world examples.
All right, example one. Let's say you've got a bottle of water and you seal the cap on tight. Inside that bottle, two things are happening constantly. You've got some water molecules that are like escaping the surface of the liquid and turning into gas. That's evaporation. But at the same time, you have gas molecules that are bumping around and diving back into the liquid. That's condensation. Well, when you reach equilibrium, the speed of evaporation exactly matches the speed of condensation. For every molecule that jumps out, another one jumps back in. It's a perfect exchange.
And this brings us right back to our ice cube. Think about it. If you have a perfectly insulated thermos, like a really good one, with ice and water right at 0 degrees Celsius, what's happening? Well, the ice is melting into water, and at the very same time, the water is freezing back into ice. When those two processes, melting and freezing, happen at the exact same rate, you've hit equilibrium. The total amount of ice and water doesn't change, even though on a molecular level, they're constantly swapping sides.
So this leads to a really important point. This whole idea of balance, of equilibrium, can only happen in what we call reversible reactions. See that double arrow? That means the reaction can go forward, from reactants to products, and backward, from products back to reactants. It's a two-way street. Compare that to something like burning a piece of paper. That's irreversible. It's a one-way trip. You can't unburn the ash back into paper, right? So if you don't have that two-way traffic, you just can't have equilibrium. Simple as that.
Okay, so we've got the general idea of balance down. But this is chemistry, so you know we've got to put some numbers to it. How do we actually quantify this stalemate? Well, to do that, we need to learn the rules of the game. And it all starts with something called the law of mass action. Now that sounds super formal, I know, but the idea is actually dead simple. It basically says the more stuff you have, the faster the reaction goes. Think of it like a crowded dance floor. The more people you pack in there, the more likely they are to bump into each other, right? Same thing with molecules. The higher the concentration, the more stuff you have packed into a space, the more they're going to collide and react. More stuff, faster reaction. That's it.
Okay, now watch how we can use that simple idea to build something really powerful. So the forward reaction speed depends on our reactants, A and B. Makes sense. And the backward reaction speed depends on our products, C and D. Got it. But what's the magic moment? It's at equilibrium, where those two speeds are exactly the same. So if rate forward equals rate backward, we can just set their equations equal to each other. And then with a tiny bit of algebra, just moving things around, we end up with this amazing ratio. The concentration of the products on top divided by the concentration of the reactants on the bottom.
In that ratio, that's it. That's the famous equilibrium constant, or Kc. And this isn't just some boring formula to memorize. This is like a single magic number that tells you the entire story of that reaction's balance point. If Kc is a big number, it means the top part of the fraction is big. You've got a ton of products when things settle down. If Kc is a tiny number, it means the bottom part is bigger. The reaction prefers to hang out as reactants. It's like a unique fingerprint for every single reaction.
Now this Kc has a few key characteristics you gotta know. First, for any specific reaction, its Kc is constant as long as you don't change the temperature. It doesn't matter if you start with a little bit of reactants or a whole lot, it'll always find its way to that same ratio. And what about catalysts? You know, those things that speed up reactions? Well, a catalyst is like a shortcut to equilibrium. It gets you there faster, but it absolutely does not change the final destination. The value of Kc stays the same. The one and only thing that can actually change a reaction's Kc is temperature. That's the big one.
Okay, next section. Now that we know the rules, it's time to figure out how to push the system. So, if every reaction has this natural balance point, this Kc, are we just stuck with it? Or can we, poke the system a little? Can we manipulate it to get what we want? Well, the answer is yes, and this is where chemists get really, really clever.
The secret is something called Le Chatelier's principle. Honestly, you can just think of this as the ultimate cheat code for chemists. What it says is basically this. If you have a system that's happily sitting at equilibrium and you do something to mess with it, you poke it, you change something, the system is going to push back. It will shift its balance to try and undo whatever you just did. It's like it has a mind of its own.
So rule number 1, concentration. Let's go back to that idea of a balanced scale. Imagine you dump a bunch of extra reactants onto the reactant side. What happens? The scale tips, right? It's out of balance. So how does the system fix it? It shifts forward. It starts working overtime to turn those extra reactants into products, trying to level the scale back out. And of course, the opposite is true. If you were to dump a bunch of products on the other side, the system would shift backward to get rid of them.
Okay, rule number 2, temperature. This one's cool. The system basically treats heat as if it's a reactant or a product. So take an exothermic reaction. That's one that releases heat. In that case, you can think of heat as being a product. So what happens if you crank up the temperature? You're adding more product. The system goes, whoa, too much product, and shifts backward to use up some of that extra heat. For an endothermic reaction, which absorbs heat, it's the exact opposite.
And rule number 3 is for gases. Pressure. This is all about space. When you increase the pressure on a system of gases, you're basically squeezing everything into a smaller box. The system doesn't like being squeezed. So to relieve that pressure, it's going to shift to whichever side of the reaction has fewer gas molecules. Why? Because fewer molecules take up less space. It's literally trying to make more room for itself. Decrease the pressure and it'll shift to the side with more molecules to fill up the extra space.
All right, final section. We've got the theory, we've got the rules, but what's the point? Let's see how equilibrium works in our world. And to do that, we're going back to our starting question about fertilizer. We're going to look at the Haber process, which is maybe the single best example of how these abstract ideas have a massive, massive impact on all of our lives.
So the whole challenge here is how to make ammonia. Ammonia, NH3, is the essential ingredient for almost all modern fertilizer. The reaction itself seems simple enough. You take nitrogen gas from the air and react it with hydrogen gas. The problem, as you can see, it's a reversible reaction, and it also happens to release heat, so it's exothermic. So the big puzzle for chemists was, how do we use everything we just learned, Le Chatelier's principle, to rig this game in our favor and get the maximum possible yield of ammonia?
And this is where it all clicks into place. It's like a masterclass in applying Le Chatelier's principle. Let's break it down. First, concentration. They're constantly pumping in fresh nitrogen and hydrogen. What does that do? It pushes the equilibrium forward. Next, pressure. Look at the reaction. You have 4 moles of gas on the left and only 2 on the right. So what do? They crank up the pressure a lot. That squeezes the reaction and forces it to the side with fewer gas molecules, the product side. And finally, temperature. Since it's an exothermic reaction, decreasing the temperature favors the products. But they have to find a sweet spot, a temperature that's low enough to get a good yield, but high enough to keep the reaction from being too slow. It is an absolutely brilliant piece of chemical engineering. And seriously, the food on your plate tonight is probably there because of this process.
So there you have it. From a melting ice cube all the way to the giant industrial process that feeds the world, this idea of equilibrium is just fundamental. It's this constant, dynamic dance between opposing forces, and it explains how systems react when we mess with them. So I'll leave you with this to think about. Now that you know the rules of chemical balance, where else do you see it? Think about economics with supply and demand, or even in biology in our own bodies. The world is just filled with these systems, all trying to find their balance. Thanks so much for joining me for this one.
Thank you for watching my video. Please like, subscribe and hit the bell icon.